Okay, gentlemen, let's take a look at solving some trig equations with identities. So just as we had seen in class 13, where we were doing trig equations, there are going to be some identities in them, where we're going to have to flip them with our double angle formula or sum or difference formula, or flip them around so that they're able to be solved as we did in class 13 with quadratics. So first, I'm just going to take a picture from the notes that we saw from 2 days ago, the double angle formulas. Those are the ones we use more commonly, so I just put them up there just for us to reference as we go through the notes. And just as we did before, we want every trig function to match in order for us to solve, just like we're going to get everything in terms of x, right? We don't want like a y floating around. We ideally want everything in terms of x. We use our double angle formula or the sum and difference one to get them all to be the same. And then what's our steps? Isolate the trig function and find the angle that gives us that ratio. So we're using our arc sine, arc cosine, whatever. The other formulas we could use up here, the other important ones are sine squared plus cosine squared is equal to 1. And then we have two other ones that come from that, right? And we divided everything by sine squared, and we got 1 plus cotangent squared is equal to cosecant squared. And then we did the same thing where we took that original equation and divided it by cosine squared and got this. Tangent squared plus 1 is equal to secant squared, right? And as you can kind of tell by the way I did it, I have this memorized, and then I get the other two just from doing those steps. To me, it's a little bit easier to only memorize that and go from there. All right, so this is what we're looking with. Let's go from here and kind of work through these nice and slow. Okay, so here to start, we see we have cosine of 2x minus cosine of x. So right away we see we have a double angle formula in here, and we got to use one of these. Okay, and as we said in here, we want to match every trig function. So we have a cosine 2x and then a cosine x. So let's try to get it in terms of cosine so that we get rid of this, but we're still with cosine. Okay, so let's zoom in over here. So we're not going to use this one because there's a sine. You can see right here there's a sine in there, and I don't want to have to deal with having a sine and a cosine. I ideally want everything in terms of cosine. Here's another one with sine, and I don't want it with sine. We want it to all to be cosine. So we're kind of left with this is the only one we can use, this one right here. So it kind of just falls out. We know we have to use that one because it's the only one that keeps it in cosine and gets rid of the double angle. Okay, so 2 cosine squared theta, or in this case x. 2 cosine squared x minus 1. So I just do a direct replacement of this into here. Okay, and then we have minus cosine of x is equal to 0. Okay, let's kind of drop the parentheses and rearrange. 2 cosine squared of x minus cosine of x minus 1 is equal to 0. So now I just wrote it in the correct order. As we saw previously, this and this we want to replace into an x squared and an x, right? We're replacing our trig functions into something we know. 2x squared minus x minus 1 equals 0. So now it's a quadratic we've seen before, and it's easier for us to solve. We want two numbers that multiply to a times c, negative 2, and that add to negative 1, and those are negative 2 and positive 1. So we do our AC method, 2x squared minus 2x plus 1x minus 1 equals 0. So I just wrote it out in 4 terms. We do our grouping, 2x, and I'm left with, that's my GCF on the left 2. Take out 2x, and we have x minus 1. Take out a positive 1 because I want the x minus 1 to match, and I get 2x plus 1 and x minus 1 equals 0. Easy factoring. Now, I usually replace it into its cosine form now, but you could wait until you solve. But I'm just going to do it here. 2 cosine of x plus 1 and cosine of x minus 1. And they're both equal to 0. Right? So I just set each factor equal to 0, and I replace the x with a cosine of x. We've seen that before. I solve, pretty simple. I get cosine of x is -1/2, and I get cosine of x is equal to 1. All right, so usually I do this in the beginning, but we look here, 0 to pi, I'm looking at quadrant 1 and quadrant 2 only. Okay, cosine equal to 1. We know that that is a quadrantal, and cosine is my x value. So where is x1? If I were to have like a little unit circle here, right here, that's 1, 0. This has an x value of 0, x value of 0. This one has an x value of -1. So the only spot I'm at 1 would be right here. We want to fall within our range, so it would either be 0 or 2 pi or 4 pi or 6 pi, but to be in our range, we're going to say it's 0 radians. Okay, now looking at the second one, I'm negative. Right, I'm negative in this, so this tells me I'm in quadrant 2. I'm going to draw my little reference triangle in quadrant 2. Here's my theta. As if I were in quadrant 2, cosine tells me this is 1 and this is 2, adjacent and hypotenuse. If this is a right triangle, what is across from the 1, that angle's got to be 30, which means this angle's got to be 60. But I'm in quadrant 2, so really it's going all the way through quadrant 1 and over to here, which means I'm actually 120 degrees. 120 degrees into radians is 2 pi over 3 radians. So those are my two answers right there. Okay, did the end of that a little fast, but we have seen this before, so hopefully it kind of comes back to you. Okay, so those are our two answers right there. There's the first one. Let's look at the second one. Again, we have the same range, quadrant 1 or quadrant 2. Okay, we see here another double angle. Now there's only one thing we can substitute with sine up here. There's only one of them, 2 sine theta cosine theta. So here's my 2, and I'm replacing that with a 2 sine x cosine x. I use my double angle formula for sine to get that what is written in blue. Okay. Now I gotta distribute my 2 into my equation. Now it's just 2 times sine times cosine, so really it just kind of becomes a 4 sine x cosine of x is equal to 2 cosine of x. Okay, now unfortunately I have a sine and a cosine, but nothing squared or anything, so it looks like I should be able to kind of solve this. Let's bring the cosine over, and now I have 4 sine of x cosine of x minus 2 cosine of x is equal to 0. Okay, so now I brought that over. Let's look at what we have. We have a 4, a sine, and a cosine, and then a minus, and then a 2 and a cosine. So there's only one thing I could do here, and that's take out a GCF. Whenever I'm trying to factor, that's my first step. When I do that, I'm left with a, well, taking out a 2 from here leaves me with a 2 sine of x, and the cosine I took out, minus 2 cosine. I took that whole thing out, so I have that one little placeholder. All right, so I actually have this broken down into two factors. 2 cosine of x is equal to 0, and 2 sine of x minus 1 is equal to 0. So just as we had seen on the first day, these are actually linear. This is, I think, it's class 12 or something like that. So these are linear. So there's no squaring. It's a little bit simpler. Cosine, if we divide both sides by 2, I get 0. And then we see over here, I can pretty easily see I get sine of 1/2. Right? Add over the 1, divide by 2. So again, we kind of have the same thing. So I'm going to draw this a little bit larger. Here's quadrant 1, here's quadrant 2. We know we're in there because of this. Now, when is cosine equal to 0? We saw that. Here was what we had before. Oops, my apologies. Here was what we had before. This was 1, 0, right? So that was when it was 1. We're looking for when it's 0, which is up here or down here. Problem is, though, we don't need the down part. We only want up. We only want up here. We only want the parts up here. So that tells me my answer here is 90 degrees or pi over 2. Right? When is cosine 0? That is a quadrantal. And it is my x value. We know that. So up here, x value is 0. And I don't want this one because I want to be above. I want to be in this area. When is sine a half? Positive, so that means it's in quadrant 1. I'm drawing it as if I'm in quadrant 1. There's my theta. Sine is opposite over hypotenuse, so I have my 1 over 2. What's opposite the 1? That's always 30. We know it's a 30, 60, 90. Changing that to radians is pi over 6. So those are my two answers there. Okay? Again, we got to keep in mind our range, and then we got to know our arcs, our arc sine and our cosine. Okay, let's do one more, and then the rest you guys can do on your own. Let's look at this last one. Okay, so now we have a cosine squared and a sine squared plus sine. And we have our range over here. So we got to figure out what to turn it into. So I have two things I could use here, either this or this. Both of them are squared. All right, so we say, well, it's not, if it was a plus sign, cosine squared plus sine squared, I could just replace it with a 1. That would be amazing. But that's not the case. It's minus. Okay, now which one do I want to turn? What do I want to flip? This cosine squared into sine squared, 1 minus sine squared, or this sine squared into a 1 minus cosine squared? I look up here. I got to use one of those. So if we look over here, here's a sine squared. If I replace this with 1 minus sine squared, they all match. If I replace this with a cosine, these match, but then this one does not. Okay, so I don't want to replace this one, because if I replace this one with 1 minus cosine squared, I have an outlying sign. I don't want to do that. If I replace this with 1 minus sine squared, all three will match. So that's ideal for me. Okay, so I'm replacing this 1 cosine squared into a 1 minus sine squared of x. Okay, and when I do that, I just leave everything else the same. So now I have over here a minus sine squared x plus sine x. Okay, so here we go. And now I can kind of just drop the parentheses. I have 1 minus sine squared of x minus sine squared of x plus sine of x, right? And essentially it's equals 0. It should be there, equals 0. Okay, so now let's start to combine what we have. I'll make this a little neater. We have two of these minus sine squared x's. So I have 1 minus 2 sine squared x plus sine of x is equal to 0. Rearrange it, minus 2 sine squared x plus sine of x plus 1 is equal to 0, right? That's a positive 1, so I just rearranged it. Now the problem is I hate dealing with quadratics with a negative in front. So if we were to take the whole thing, both left and right side, and multiply it by -1. I'm doing the same thing to both sides, so I'm allowed to do that. It comes a lot nicer because then this becomes 2 sine squared x minus sine of x minus 1 is equal to, well, 0 times a -1 is just 0. So I get the same thing. I'm still allowed to do this. Okay. So now let's solve this. So again, we do the same thing. We take this, make that an x squared. We take this, make that an x. And we have 2x squared minus x minus 1 is equal to 0. Two numbers that multiply to -2, my AC method. And add to a -1, -2 and +1, same as we saw above actually. 2x squared minus 2x plus 1x minus 1 is equal to 0. Take out a GCF, 2x, x minus 1, take out a 1, x minus 1, and I have 2x plus 1, and an x minus 1 equals 0. Okay, did that a little fast, but we actually just saw that same exact equation up above, so we factored this already. Okay, Right, so we replace the cosine squared, not the sine squared, because now I got all three to match. Rewrote it. I don't want a negative in front. You could do it, but I didn't like the -2 as my a value, so I times everything by -1 and made it something that's a little bit easier for me to do. So now I have 2 sine of x plus 1, and, well, I'll do it like this, and sine of x minus 1 equals 0. Okay, all right, so we have 2 sine of x plus 1 equals 0, and we have sine of x minus 1 equals 0. Easy to see that this becomes sine of x is -1/2, and sine of x is 1. Okay, now let's look at what we have over here. Take this, draw it over here. Oh, there should be a less than or equal to x over there. My apologies, that should say less than or equal to x. That may be another typo down below. Okay, so now I'm looking at either quadrant 1 or 4. Okay, this is negative. Tells me I'm in quadrant 4, because everything's positive. Sine is positive in quadrant 1. This is equal to 1. Oh, that means I'm a quadrantal. So I'm looking at my quadrantals. That's a y value. So where is sine 1? Y value of 0, y value of 0, y value of -1. This is my y value of 1. Where is that at? 90 degrees, which is pi over 2. Looking at pi over 2, is that in my range? Yeah, that's in my range. That should say less than or equal to. Right in between here, it should say less than or equal to, so it would be in my range. All right, now I'm in quadrant 4 here. Let's draw my reference triangle as if I'm in quadrant 4. Sine is opposite over hypotenuse. Opposite over hypotenuse. What is opposite the 1? Well, we just saw that. That's 30, which is pi over 6. So my answer is pi over 6. But I'm in quadrant 4. I don't want to go all the way around because I don't want to go through unallowed territory. So it's pi over 6 or 30 degrees in quadrant 4. Not allowed to go all the way around, so I have to go this way. So I'm actually negative pi over 6. So there's my answer, negative pi over 6. All right, so hopefully this is kind of just brushing back the things we had done in class 13 and 12, which were linear. And the only thing we got to do is make sure, substitute your double angle or whatever you have with something that's going to make all the trig functions match. Okay, and if we scroll down, just making sure, here we go, keep a track of your range, keep track of your range. Again, I knew there was another typo here. Just make sure this should say less than or equal to. So for number 3, I forgot to put that in there, my apologies. So that should say -90 up to 90, or pi over 2 to negative pi over 2. And then we have this one for 4, and this one for 5. Okay, secant squared and tangent squared, you're probably going to use this one, something up here. Okay, so good luck.